Thank you very much, tech team, for getting us back on. So my name is Denis Gray, and I'm going to be talking about new occultation technology and giving you a little bit of a rundown on what I've bought recently. But first, I want to talk a little bit about, thank you, what are occultations in the first place, or not everybody's probably familiar with it, and I'll talk about the quest. So it's kind of like anybody who's interested in occultations has this nirvana that they seek. They seek to be able to go out, plunk a telescope somewhere, have it automatically find the target, and then just observe whether or not it turns out or not. That never works. So we'll talk about you know, what we're actually trying to do and what kind of the ideal system is, and then we're going to compare and contrast two opposite pieces of technology. Both are recent. One I'm calling cheap and cheerful, and the other one I'm sort of calling all-in-one or next generation technology, and we'll talk a bit about that. So first and foremost, what are occultations? So an occultation defined is an event that occurs when one object is hidden by another object that passes between it and the observer. An example of this would be, hey, that 2017 occultation of the sun by the moon was a very big event. And not everybody calls it by its proper name. Some people have been known to call it an eclipse. But it is an occultation by definition because it's hidden. And I think one of the key words in this is event. It is an event. This is event astronomy we're talking about here, and we'll talk a little bit about what's involved with that. Now, in terms of astronomy, we have many flavors of occultations. There's not just one. It's not just that one that is also known by eclipse. But generally speaking, the moon gets involved a lot. Many times during its monthly orbit, the moon will run over stars. You can see here's a frame grab from an occultation, and that star there is just about to be run over by the edge of the moon. And when it does, it blinks out. It blinks out because the star, at the distance that it is essentially a point source. If you look at it in a telescope, it looks like it's not quite a point source, but at the distance it is compared to the moon, it is a point source. So it's like basically a tiny little extremely bright pin on the edge of the moon, and as soon as the moon's edge goes over it, boom, it's gone. So from one frame to the next, you'll see most stars will blink out immediately unless they're an extremely large star like an Antares or something like that. The other flavor of occultation of stars by the moon is what they call a grazing occultation, where a star sort of just edges through the North Pole or the South Pole of the moon. And what you see there is lunar topography revealed, in the sense that hills, valleys, mountains, and so forth will cause the star to blink on and off. And this study, for many, many years before we had lunar satellites that measured the moon to within millimeters precision, was our best way of understanding what they call the lunar limb profile. And some people still do those occultations now. We also can see the moon running over planets. That's kind of a cool event to watch. So you'll see Saturn get closer and closer to the edge of the moon, and then it'll take out one half of the rings, and it'll take out the planet itself, and then the rings finally disappear, and then in reverse. I've seen Venus get occulted by the moon, and that's actually a cool event. You can actually observe that with the unaided eye, where you see this really bright planet being run over by the crescent moon, and eventually it blinks out, but it will, because the Venus is actually relatively large compared to the edge of the moon, it actually takes a bit of time to go away. The other really interesting one is sort of occultation of planets by other planets. This is actually something where you need to have exactly the right geometry, where a planet like Uranus will be occulted by another planet like Saturn. So first of all, they've got to be close in their orbits to even have a chance, and then it's got to be, Earth has to be in exactly the right place where everything lines up. So there's like 3 or 4, 5 events like that per century, and you can look up those, and if I'm not sure when the next one is coming, but those are pretty exciting. And then also another occultation flavor is mutual occultation of Galilean and moons. So what happens is when the Galilean moons are precisely aligned with Earth, which happens in 2 seasons separated by about 6 years, when those moons cross each other, you'll see brightening and dimming of those moons as they essentially overlap one another. And our favorite, and the one we're going to be mostly talking about tonight, asteroid occultations. Now, asteroid occultations is a branch of citizen science. It's one of the remaining areas in astronomy that amateurs are really able to make a big contribution. And in fact, most of the research that's happening here is either participated in by amateurs or driven by amateurs. You know, one of the big projects you probably heard about is New Horizons recently. New Horizons was trying to pick its next target. So one of the opportunities was to use an occultation of a Kuiper belt object that was able to pinpoint that object's position and help determine where New Horizons is going to go next. So when you're observing an occultation and you're doing the timing, we can add these little pieces of information to what we know about the universe. And that's sort of the definition of science. It's an incremental thing, we're adding a little bit. But by knowing when that event happens, we can use mathematics and other information to determine exactly where was the star at that moment of the occultation. Similarly, we also know exactly where the asteroid was at the moment of the occultation. And using that information, along with some other stuff that we have, we can determine the shape, size, as well as sometimes the volume of the asteroid, which leads to its density, which leads to, and combined with its spectra, leads to information about the origins of that asteroid. So all of that stuff is coordinated by a group of passionate amateurs at the International Occultation Timing Association. They have an annual, I think they have $10,000 in their bank account and an annual budget of $3,000 or something like that. It's truly a labor of love kind of organization. So why is this fun? Well, it's event astronomy. It's astronomy as a sport. In order to observe an occultation, you have to be in the right place, the right time, and you need to have the right rig. So it's essentially putting together all of your skills, all of your experience as an amateur astronomer to try and pull all that together. And what I've noticed is that the universe does not wait for you. It will go ahead and it will do the occultation exactly when it wants to, whether you're ready or not. And that is sometimes frustrating. Sometimes it's extremely frustrating, but it is essentially the nature of the sport is that sometimes you succeed and sometimes you fail. The best events are tracked through IOTA and its members and their participants there. And generally, what I'm looking for is a reasonable time. I'm not one of these people who's ready to stay up till 3:30 in the morning to do this. My work life is too much. It's got to be a relatively bright star, so it's relatively easy to spot and find. And ideally, you want to have a good magnitude difference. So you can have an asteroid occultation, and you can have an asteroid occult a star perfectly well. But if the asteroid is 11th magnitude and the star is 11.1 magnitude, well, you're not really going to notice much of a difference there. So that also makes a difference. And then, you know, all of these things have to be put together. And sometimes you'll find that the universe will conspire to give you 3 events in 24 hours, and other times the universe will conspire to give you no events in 3 months. And then you have to, of course, add the weather factor, which I think is threatening this week's really good occultation, and so on it goes. So it's part and parcel of that process. So the objective when you're trying to measure and observe one of these occultation events is to get your location on Earth, your disappearance or perhaps a dimming time precisely, and a reappearance or rebrightening time precisely, and submit those 3 key pieces of information to IOTA. They're going to collate your observations with other people's observations, and you're going to end up with something that's like this. So here you've got a whole bunch of individuals with a whole bunch of telescopes all looking at the same event at different times. So this one here, this bright blue line, they could have been in Europe. And this one here, this yellow one, they could have been in California. This one here, I would say they're in Hawaii, but that's not possible because that would have been daytime. But in any case, all of these observers spread out across many, many different locations, but we know where they are relative to this asteroid's shadow that's basically passing across the Earth. And when we put all their disappearance times and their reappearance times, so this has disappeared here, reappeared here, disappeared here, reappeared here, we're able to get a shape of the asteroid in 2 dimensions. So this is one of the most successful ones that's been done in the recent times. So this is a binary asteroid. This part of the binary looks, fairly round-ish. This one, it's got a huge divot taken out of it, and that's one specific, sort of slice through these 2 asteroids on a specific date and time. And if we're able to combine this information plus other informations, you can actually over time build up a 3D profile, because one of the other things we know about this is the rotation period of these 2 binary pieces is reflected in the light curve that comes from the asteroid. So you put all this information together, we can learn an enormous amount about these objects without actually really being able to see them, which is kind of cool. Although I would love to see a space probe go and visit this system, because I think that would just be the coolest thing to see these 2 rotating through space. I'm sure it's a bit of a mess. So that's the objective. So how do we get there? So you need GPS level information. So in order to know where you are precisely, you need to have some GPS information, which is your latitude and longitude on Earth, precise location, and you need to have precision in time. So all of those measurements that we're looking at here, the reason they're so nicely coordinated and they're so tightly cut off here is GPS level measurements. You need some optics. You need to have a telescope. Generally speaking, a shorter focal length is better than a longer focal length because you get a bigger field of view, and the light from the stars is concentrated onto fewer pixels, which allows those pixels to give you a better signal to noise ratio. So you're able to see when the asteroid dims or blinks out. So that's something to keep in mind. And then you need some sort of recording mechanism to put all that information into a place so that you can record the ins and outs and so forth. Now, over time, the state of the art has changed. So when I first got into this back, early in the 21st century, the essential process was you're going to use a map. You're going to go and get a topographical map, and you're going to go and find the location of that country road where you were at the 4th concession, or was it the 7th concession? I can't remember now. And you're going to precisely locate yourself roughly within, a couple of maybe 100 meters. That's, of course, moved towards standalone GPS devices, and now everybody's pretty well got a GPS on your phone. So you can get very, very accurate location information. Telescopes, obviously have been revolutionized in a lot of ways by go-to technology. So the dream is that you can plunk the telescope down. In some cases, you push a button or you turn it on, and it will figure out where it is, and it will come up and be able to point to the location of this event very, very quickly. Video technology has changed very quickly, and when we first started to work with occultation technology, we were always using analog video, and analog video was pretty well limited to sort of the screen size of the day. So the PAL or NTSC standard was sort of like 640 by 480. That was a standard 4:3, what your old television would have looked like, and that was part and parcel of that whole analog technology. We moved partway from that by recording this analog signal on a digital video method so that we could translate it more easily into computer language. But now we've moved towards pure digital video recording. So now all of your cameras, like if you're using a camcorder or DSLR to do recording, you're recording digitally, and there's no intermediate analog video happening in between. And then in terms of recording, it used to be that people would have a voice tape recorder, and they'd be listening to a time signal from Colorado beeping on the radio, and they would say, out, in, and then they would go back and they would have to interpolate, exactly when did I say out and when did I say in, and knowing that I'm a little slow on the uptake, I have to add 0.2 seconds to that, because that's my personal, what we used to call a personal equation, to record the time that these things would happen, because all of this was done visually at the beginning. So what's now happened is we've added video overlay systems to add that GPS information to the video, and what we'll be talking a little bit about tonight is integrating all of that together into one camera. So, how many of you are excited? Want to get into this? Yes? Sure, thank you. All right, so cheap and cheerful. You want to start cheap and cheerful. So there is a new offering kind of thing that's been put together by our friends at IOTA, the International Occultation Timing Association. They're all about encouraging people to get involved, and they have their own emailing lists, and they promote events, and they're generally a very nice group of folks. And they have created this thing called the Night Eagle Astro Camera Kit. And it's based on an interesting camera. I've never heard of it before. I happened on this, which is a night vision drone camera. So this is an extremely lightweight camera designed to be absolute minimum weight, run on a drone, and go over people's houses and spy on them in total darkness. So it's got really, really good response and so forth. So essentially, the folks, they're identified that it can do integration, which means stacking frames up to 16 frames to intensify the signal-to-noise ratio. And IOTA's put together a kit for $179, which is essentially giving this little cheap and cheerful camera here, this kind of off-the-shelf camera. And what they've done is they've put together all the little bits and bobs and spacers and a focal reducer and so on to allow you to install it on your telescope. So this is what the finished camera would look like, and this is all the bits and bobs that you would get in the package that would allow you to do that. So the overall kit is available from IOTA. They actually will sell it to you, and they'll ship it to Canada and everything like that. So this is sort of the state-of-the-art for cheap and cheerful. Now, before this camera came out, you could also get other video cameras that would be, this is an analog video camera. You can get other cameras, kind of similar price point, but what I think is really exciting about this one is the sensitivity's just gotten better and better and better. So they're getting like 11th, 12th magnitude with, reasonably inexpensive scopes using these kinds of cameras now. So that's really, really exciting. The other thing you need with a cheap and cheerful system is the video time inserter. So we talked about the need to know your GPS time as well as your GPS location. And what it does is it takes your GPS information and it overlays it right on the video signal so that the video output has already got the timestamp put in there. And the limitation is going to be the precision of the video. So the timestamp is going out there as fast as it can, and the video is running at 50 frames a second or 60 frames a second. So that's sort of your time resolution, is you can't get any more fine than that. The universe is a little bit more, has more precision available for it, but that would be that. And then you need some sort of a video recorder. Now, one option for recording this video as it's happening is a DV camcorder, digital video cassettes, and those have kind of fallen out of use pretty well. They're not antiques. They're still kind of high tech, but you certainly can't buy a new one. But you can still get some of them available on eBay. Now what IOTA's recommending is that you go to the field with a laptop and you have a USB video capture device, and they have a specific package of software, most of it free, which allows you to keep your video streaming into your computer and not lose any signal due to compression. So a lot of video software will look at a picture and say, most of that picture is black with just a few spots on it. So I'm just going to scrunch all that down because it's just mostly black. And that's not what we want, because that's the part we're interested in, is when does it turn black and when does it not turn black. So that process of using that, and there's some technical guidance and so on, lots of helpful information there. And you follow that helpful instructions and you will get pretty high resolution with that. The other piece, and the cheap and cheerful option, is you need the analysis software to sort of read this video file. So you record this video file, you dump it onto your hard drive, and it's like, okay, there it is. Now what do I do? So what you do is you open up in this program called Tangra, which is freeware, and it reads both AVI files, which is a common video format, and then this astronomical video format, which is being worked on here. And that Tangra can actually read the timestamp from the video time inserter, and it will actually give you an analysis of the disappearance and reappearance. It will actually show if it's a step disappearance, which can sometimes happen if you've got a very close binary star, and it's free. It's very, very cool software, and well done. So that's cheap and cheerful. So if you want cheap and cheerful, that's the option. Now, the new option, which I purchased recently, is the next generation sort of video option. So this is a specific camera from QHY called the 174M GPS, which is a much larger imager. So this is 1920 by 1200 pixels versus that's kind of a large video camera. 640 by 480 is also possible. So it's like it's twice or 2 or 3 times as big, but it means like 4 or 5 times as much resolution. It's using USB 3 video, so it's actually recording on it's taking advantage of the fact that USB has a much faster rate of data transmission than USB 2, and so it allows it to actually transfer these large files at high rates. It's fairly heavy. It's about a half a kilogram, 1 pound. And the frame rate that it does, as opposed to a video, where a video frame rate is 60 or 50, whether it's got anything to show or not, that is the definition of the analog standard. So if depending on whether it's NTSC or PAL, you just get the frame rate you get. Here, the frame rate really depends on how fast the frames are being received by the computer. So you can tune it to get the frame rate at the best possible combination of frames and recording to suit your computer. So theoretically, you can get much, much higher time resolution on these events than you can get with an analog system. And then because it's got this bigger imaging thing, it also has a bigger attachment, which is an M42 or a T2 thread. So now I said to Paul when I put this presentation together, that we would have a chance to, show some stuff here. And I received this about 10 days ago, and as most of you know, we have not really seen the sky at all. And so I have verified that this camera, when plugged in, works. And I can say for a fact that it will image stuff when it's plugged in. That's the extent of my testing now. However, other people have had better luck than I've had, and this is a sample of the output that you would be able to get. So what you can see down here is, essentially the time signature here, and that's, the hour, minute, second, and partial second there, and between the 2 frames. So this event happens, in there, and this is an example of some integration going on. So he's actually taking a bit more time to get more sensitivity, and he's getting down to 12th or 13th magnitude stars here. Some of these more dim ones are very, very sensitive. And you'll notice that the quality of this image is a little icky. If I was an astrophotographer, I would say, well, this is garbage. I'm going to throw this out because obviously I can't stack that or do anything with it. From an occultation perspective, you really don't care. The point is, does that disappear or not? And if it does, great. If it doesn't, that's also data. And so you're simply monitoring to see whether it disappears or not. You're not so concerned about whether or not it's pretty or not. Now, it is important that the stars be, your telescope be well collimated, that the stars be, focus up crisply and so on, but that's all about seeing what you're trying to see. And this shows us the actual frame count that's being imaged here in terms of the frame. So you're seeing good, results here. It's going deep, and this is big. Like, this is actually, quite a big field of view, and I'm going to hopefully get some measurements of what that looks like. So this is what it looks like the camera, and we'll have a look at it a little bit out there. So this is for those of you who are CCD imagers, this is actually a variation on an existing QHY model. So there's another version of this that doesn't have the GPS option, but is essentially the same kind of camera. So on the back here we've got the USB 3 port, we've got a power port for running the thermoelectric cooling, we've got a filter wheel connector, we've got a guide port. So all of that stuff is standard, and then what happens is if you buy the GPS model, you get this little GPS antenna mount here added, and then that becomes the key difference. That plus some additional electronics in it is the difference between the GPS unit and the not GPS unit. So as astronomical video cameras go these days, 2.3 megapixels is pretty small, but still useful. You can still do a lot of good things with that. So drum roll, please. Let's look at the money piece here, because that is important. So the cheap and cheerful option, if you don't have a timing unit, so it's about $500 US. So there's bits and bobs you need to put all together. And thanks to Steve Conrad who put this comparison together, looking at that. So if you have your basic camera, you have your GPS, you've got your cables and so forth, and you can then essentially work with that in the field. And I have an example here. This is my rig from before, where I have my field unit that I would use to do analog video recording in the field with a camcorder, with the screen, the monitor to see what's going on, and so on. Now the QHY GPS here, the camera is a lot more expensive. The GPS timing is built in though. The power supply is not required because you can run this off of your computer using the USB port. There's no video input required, so you don't need any of that. The focal reducer is going to be bigger because the camera is bigger. So you can use a very small focal reducer on the small cameras, but for these larger cameras you need a bigger focal reducer, so you need to spend a little bit more money on that. So we're looking at about 1.5 times more to get this sort of next generation technology. And the key difference really is its usefulness for other astronomical applications. So my goal for this is not to have to take the whole case with me every time I want to do an occultation, that I could actually go and do some imaging type applications with this, and then when an occultation opportunity presents itself, just turn on my GPS option and let it go. It's somewhat future-proofed in the sense that this is digital imaging. I think has reached a certain point of maturity where I don't think the formats are going to change that much. It's producing FITS files, it's producing an SCR file, so I believe that the output from the camera, no matter which one it's doing, should be there. But the price difference, 1.5, 3 times more, depending on what you're going to do. So that is one of the big differences there. So you've got a much bigger camera, all digital, smaller footprint in your equipment case, but you're going to have to spend more money for it. So that becomes the key thing. So I'm just going to ask you to turn up the lights here, and I'll just sort of show what this looks like. So this is my occultation camera here. So right here on the front. Now I'm using a C8 here, which has got a hyperstar lens on it. So one of the things that, if you know how a Schmidt-Cassegrain works, and normally the light comes in here, hits the mirror, hits another mirror here, and then goes out the back. And that system is an f10 or an f6.3. Now with a hyperstar lens here, what happens is it comes in, hits the mirror at the back, and then it hits a lens here where it's corrected, and then it comes out the front. So the camera is mounted on the front, and it looks a little ungainly because I'm always thinking, well, if I just do this, I'm going to break my corrector plate on my camera, and that will be the end of that particular telescope. So generally in the field, we always wrap this with a dew shield in the field. But the idea is that you have this camera which actually doesn't add very much at all to the central obstruction. It's like literally almost exactly the same footprint as the mirror originally was. You just lose a little bit, and then you've got your cable coming out the side, and that's it. So it works as a system. And the cool thing is that it's a very very fast system. It's f1.9. It's a 390 millimeter. It's like basically you're getting this big telescope, and you're getting, you know, what amounts to telephoto lens style f ratios. So the theory, and one of the things I would hope to measure and share with you, is just how big a field of view I can get with this camera combined with that that telescope, with presumably some proper spacers included. So, as I said to Paul, there's probably another presentation in this somewhere. So then that telescope with that camera mounted on a go-to mount and attached to a computer, which will give me both the video and the telescope control, represents a significant reduction in the amount of stuff that I have to take on the field to actually do what I'm hoping to do with in terms of measuring occultations. And that's kind of my goal. That's what I was hoping to get for it. Don't know if I'm going to get it necessarily yet, but hope springs eternal. Conclusions pending. However, if we get some clear weather, I'm hopeful that we will have some conclusions that we will be able to share with you, and I'll try and post some of those on the list, and hopefully one of these days I'll actually even have a chance to actually record an occultation and maybe put that on the line somewhere and share some results like that. So that's what I got. Occultation technology today. Yeah. Any questions? Yeah. Yes, sir. Mr. Beaton.
How much of a big deal is it to replace the secondary mirror on your telescope there with your camera and widget?
It's pretty simple. It's got a locking collar. You basically unscrew that, and then you unscrew the protective cover from the hyperstar, and you put the hyperstar down. You put the mirror in the hyperstar dingus, and then you screw it tight, and it's locked and it's dustproof. And then you put the hyperstar mirror and you screw that on, and you're done. It literally takes about a minute once you're experienced. It's a little slower the first couple of times you do it because you're thinking, this is gonna be a disaster. But then you get used to it and it works pretty well. I can show you after the meeting for sure.
Sure.
Yeah. Yes, sir. Oh.
I noticed that in your cost analysis you did not include the computer.
Yes, that is a good point. The assumption would be that there is a computer out there somewhere.
Yeah.
It would need to be a relatively modern-ish computer that would handle the USB 3.0 well. Otherwise, you're going to get a relatively slow frame transfer, I think.
Do you recommend then that you have one that's dedicated specifically to this and not run other stuff that might be running in the background that you might be unaware of and so on? Or?
Yeah, what I read is that when you're imaging, if you want to get the best possible recording, you would basically shut everything else down during the recording part. So in other words, you fire up your planetarium program, you get your telescope pointed, and then you basically shut down that planetarium program, shut down your other stuff, and then just focus on the recording, and then tweak the capture tool to get the best frame rate with the minimum number of frames being dropped. And there's the SharpCap software. I had a very quick look at it over the weekend, and it has sort of like presets. So you can sort of say, well, if you're capturing, like one of the things that's nice about it is you can say, I want to capture, I'm going to borrow somebody's Mac here. Let's say I want to capture the whole frame. Great, that's the maximum. But I can also tell it to only capture this part, or even just that little part, because that's where the occulting star that I want to see is there. And the smaller you make the relevant part of the frame, the faster the frame rate becomes, right? So you're able to actually kind of tune that a little bit, and that would also reduce the load on your computer to make it work better, right? But it's an important variable, and that's one of those things. Like I've done some basic recording, and it seemed to work, but no real life experience to share. I'm sorry.
Okay, thank you.
Yeah.
Let's say the visual magnitude you could see through a telescope is, say, 12.
Mm-hmm.
I know you don't have any feedback because you haven't been observing because you didn't want your scope to get wet. But
Well said, well said.
do the people that sold it or others talk about that you could see brighter stars, only brighter stars than the best visual you could get, or you could see even fainter stars? Because often I find for occultations, I see one, it's great, I'm in the path, and then I look at it and it's just right at the limit of what I can see, and there's
Yeah.
a tad bit of light pollution in Bolton, so I usually sleep.
Yeah. Well, I think, yeah, what you're saying is a you know, kind of a common issue, and I've had occultation cameras that do a certain amount of integration, right? Like stacking inside the camera, and then so it stacks like 10 frames and then sends one stacked frame per 10 frames, and so you lose time resolution, but you get sensitivity. I generally find I can see more with the camera than I can see with my unaided eye, generally speaking. But can I see the target in question? So what I found with my existing rig, my limiting magnitude is like 9.5, 10. I'm hopeful that this can go much better. And I'm not sure how much of that limiting magnitude is just Toronto, but also, you know, there's, you know, one of the unfortunate things is our friends in Australia get a lot more occultations because they just have way more stars to occult, right? And so, you know, here in the northern hemisphere, you know, especially when we turn into like the fall, like the number of stars that the asteroids can fly in front of is significantly decreased at this time of year, which also limits your opportunities, right? So there's, you know, a number of factors that come into it, but I generally find the camera does a better job of showing stuff than my eye, especially these days as my unaided eye continues to go past its warranty.
Yeah, a question from the web.
Yeah.
Is it possible to attach a DSLR to the Hyperstar?
Yes, it is. It is. I have seen it done, and it because it fits a standard T2 interface, you can certainly do that. But one of the issues is that the DSLR's footprint is much larger in terms of obstruction than these round cameras. So these round cameras are actually, I think, in some ways built with the Hyperstar in mind, because I look at the footprint here and it's, you know, from here to here, it's just about practically identical. It's literally almost designed, it looks like it's almost designed for it, but I know a DSLR would stick out quite a bit on both sides there, and it would cause some obstruction that you wouldn't have with this camera. Yeah. Any other questions? Yes, sir.
So it's not more of a question as opposed to clarification. I think the Hyperstar is recommended for 9.25 and up in the SET's models.
Is that with the new Edge, Edge ones?
Yeah, the Edge, yes.
Yeah.
I don't think it's recommended for the 8-inch.
Well, this is a model that works for, this is designed for the 8-inch, but it does have limits in the sense that it doesn't have as big an imaging surface as it would have if it was a bigger telescope. So the bigger like each one of the Hyperstars, and formerly that is stole by Starizona, I think I said that right, is sort of optimized for the size of the corrector that it has to work with. So you get a bigger field of view if you go up to like a C14. I saw on the Starizona website as well that they don't currently have any fast stars for 8-inch for sale, so maybe they're rethinking that in terms of their marketing. This system also works only on Celestron scopes. It's not something that's available with Meade. And the 9.25 model, they actually had something where the mirror is bigger than the hole that's in the corrector plate. So you literally can't take the mirror out with certain 9.25 models, because if you did, you'd have to make the hole in the glass bigger. So that is like, you know, I didn't realize, you know, it's like, why can't my 9.25 do this? Well, it's actually because the mirror is actually a little bigger than the corrector plate. So anyway, all that to say that, yeah, this is a bit specialized, but you could put this camera on any other telescope, right? So the ideal is to have a short focal length, but you could put it on any other telescope that it can handle. Yeah. Any other questions? Once? Twice? Well, thank you very much, everybody. I hope to come back with results.
Oh, yeah. All will become clear. In that nice amphitheater, just plopped right in there. Well, as you can see, I've been traveling again. And they call this Namibia's, is it okay? Yeah, you're okay. Okay. Namibia's fallen star, great big meteorite out in the middle of nowhere. So I've been traveling. I started in Windhoek, right here, went down near, saw the dunes, all up and around here, and ended up in Victoria Falls. But where we're going to talk about is Grootfontein, which is where the Hoba meteorite is, about 20 kilometers west of Grootfontein. So you've seen one picture of it. We'll get to some more after a bit. There's a nice national monument there that was established in 1955, but it didn't get built until close to 1990. The landowner donated the meteorite and the land to Namibia, and a uranium company donated the funds for development of the site, including that nice amphitheater that you saw in that first picture. So this is what greets you. Better not have any complaints. It's 300 miles. And they don't have Wi-Fi, so you have to talk to each other. That's a big problem anymore, you know. Also, beware of falling meteorites, especially that one. Okay, so we all know what some of these things are. The asteroid's just going to pass by Earth. If it burns up, it's a meteor. If it hits the ground, it's a meteorite. It just stays there. It's Congress, right? Called Congress. Or maybe Parliament. Okay, now this is not to show that I was there, not proof of purchase or anything like that, you see. It's just for to show how big the meteorite really is. Okay, here's some statistics on this thing. Discovered in 1920, it's about 3 by 3 by 1 meters, weighs 61,000 kilograms. Age is, 4527 plus or minus 29 million years, and that was estimated in 1996, fairly recently, they came up with that site. It's a nickel-rich group 4b ataxite. There's only about 14 of these meteorites of this age that are known to exist. This is one of them. So it's 82% iron, 16% nickel, and around 1% other elements, mostly cobalt. And that provides something interesting later on. The Smithsonian Institute scientists concluded that the meteorite had been present, quote unquote, on the surface of the Earth for about 80 to 300,000 years, and that a layer about 27 inches thick was removed from the meteorite by ablation when it passed through the atmosphere. And that comes from Fernie. Somebody might recognize that name here, but we'll talk about that later. Things of note, Hoba from the native language means gift. It's the largest known single-piece meteorite in the world. It's the most massive naturally occurring piece of iron known on Earth's surface. Not surrounded by a crater. Its remarkable flatness of its bounding surfaces, unique among meteorites. One theory is that the meteorite shape caused it to skip along the surface of the Earth rather than crashing and burying itself. I guess like skipping a rock across water, but that's a pretty heavy one. So there it is. I just walked around it. It looks pretty much the same all the way around, starting here at, starting here at the steps. This is just side 1, side 2, side 3, side 4. It's all pretty uniform. So some analysis was done on it right away after discovery by a non-scientist, but he was very detail-oriented. And they found elongated patches of troilite, which is a rare iron sulfide. Most common mineral on the lunar surface is troilite, and it's also present in Martian meteorites. These Wittmann-Statten lines that are very often present in meteorites of this type are absent in this one. But there are some Newman lines that are present. These are just example photos. They're not from Hoba. Okay, vandalism used to be a problem, but it's very hard to do because of the composition of the meteorite. Why? A nickel-iron mass with just a touch of cobalt results in an alloy of unexpected toughness, you know, even if it is fairly ductile. So those are examples, up-close examples of where vandals have tried to get a piece of this meteorite. Somebody asked me if I brought home a piece of it. No way. You're not getting anything off of that. There's an interesting story here. The South African company donated to the British Museum a piece of this meteorite. But getting it off the meteorite was a real chore. It took 2 days for 2 natives working all the time with many hacksaw blades to get off a wedge-shaped piece about 2,500 grams and about the size of a sheet of paper, fairly small sheet of paper. And this is from Spencer from the British Museum, who then performed a thorough analysis of the specimen. The meteorite has, unfortunately, been disfigured all along one top edge by some stupid person with an oxyacetylene blowpipe. So it's tough getting a sample of that meteorite. They only seem to be 18 pieces of this in collections around the world, only totals 25 kilograms out of 61,000. So it's hard to get at. Okay, here's a little bit of the history, and this disagrees with what you find on Wikipedia. But this is an actual tale that the man who found it told, and it's in the museum in Grootfontein. He was, Wikipedia says that somebody was out plowing and they hit it with their plow and found it. He was out hunting. He noticed the strange rock, sat down on it, tried to scrape a little bit of silver under there. So he thought he got just enough off that he took in to Grootfontein. where mineralogist established it to be a meteorite. So he came home and they talked about it, and he went on with his work, and Mrs. Britz started excavating it. So she started digging and got quite a ways around digging it. So they weren't the owners of the farm where this was found. Hansen was. And after he heard about the discovery, he now claimed to be the discoverer. So he wrote to the museum saying, "I have discovered on my farm a huge meteorite, and I have digged a trench round it to find its thickness." So he wanted somebody to put a value on it. The museum replied in a rather condescending tone, "One cannot quote a price as one can for sheep or cattle." Okay, these are just some kind of random photos. This is thought to be the first photo of the meteorite. No date on that. Once the knowledge about this meteorite spread around the area, it got other people coming just to take a look at it. This man here is Spencer, who was very involved in analysis of this. And this is the International Geological Congress excursion in 1929 to see it. And this is Gordon, who did the analysis on it that I've already talked about. He was the second ever scientist to visit the meteorite in 1929. So even the New York Times gets in on this in 1929. And particularly here, again, chance has led us to the discovery of one of those mysterious messengers that come to the Earth, bearing evidence that space is not empty, but is populated with a vast multitude of small fragments. So this was in 1929. So now, who knows this man? Does anybody know for me? I thought Ralph. Anybody else? I figured Ralph would know. Okay, I just kind of came across this. He was a Canadian astronomer based at the DDO who'd been in Cape Town during the mid-50s. Well, he went back in 1966, and he and a friend drove by car, not 4x4s. And even today, on my trip, those roads are rough. You know, there aren't that many paved roads. They're rough roads. So that must have been quite the trip. And he published this article in the RASC journal, 1967. I didn't find this article until about 2 days ago. I was going to ask you if you knew how to get a hold of it, Tom. But I did finally came across it, and I haven't had time to read the whole thing. It's very interesting. He took what was considered to be the first color photograph of the meteorite and said that among the major meteorites known on Earth, few can have received less attention than the Hoba meteorite. And that's probably true, because this was in 1976, discovered in 1920, a long time in between there. They established the site in 1955, so it took a long time for people to come to the party on this meteorite. So he was president of RASC from 74 to 76. I had to consult a thesaurus for making this presentation, but he was no help at all. Often at a loss for words. Okay, so these are a little off subject, but sort of close. There's only 2 touristy photos, Paul, so. This is in Swakopmund. It's on the Atlantic coast, and this is the world's largest quartz crystal cluster on display. I thought it was pretty interesting. 14,000 kilograms, 520 million years old. This is, This is my photo here. I stole off the website because it gives a comparison of the size. It's big. You know, it's fascinating to just come up and look up at this thing. Okay, people have asked me since I came back if I did any observing while I was there. Well, kind of, sort of, one night, sort of. This is my place where I was staying at night. It's on the banks of the Quando River. You can see the river out there. Right in front of the hut, there's a deck there. But I walked out after dinner one night about 9 o'clock and was coming back to my lodge. And this path here is patrolled at night by a guard, back and forth, because there are no fences and there's wildlife around. And we had just been watching crocodiles and elephants and hippos across the river there. So I looked up and I thought, oh, this sky is glorious. I have to just find some place to look up at it. But there are lights on the path. But I found this little corner right here on my deck where this tree blocked the light. So I took a chair out there and I sat there for about a half an hour looking up. Not a good sight. I'm facing east there. There's not really, Mars is up here. Planets are over here. Until, about a half an hour I'm there, until all of a sudden I hear a splash and some rustling in the bushes. I was back in that lodge in about 5 seconds, leaving the chair. So that's my observing in Namibia experience. So just a few touristy photos. This was on an airplane flight over the coastland near Swakopmund, and those dunes look like that. They look just luscious. It looks like frosting. They're just gorgeous. Okay, here's a moon. It's a moon set over Etosha National Park. That one's taken with an iPhone because my camera lens went out on me halfway through this trip. My wide-angle lens. There's my pelican sunset. Thousands of pelicans we saw there. Pelicans. And there's my hippo sunset. So the sunsets are kind of relevant to astronomy here. Okay, so I did some digging around too to prepare this presentation, but not quite like Mrs. Britz was doing. Not digging in the dirt too much. This, I've been told, is an African goodbye. That's all, folks. Thank you for listening. So, can you close that? So how do I get that off? Any questions? Nope. Adrian.
Coolest places on Earth. Well, what was your reasoning behind going on this trip? Because normally you do astro trips, like Chile, for example.
I've always wanted to go south in Africa, and particularly Namibia. It's just always been one of those dreams to do, and this trip came up that took me exactly where I wanted to go. I saw everything I wanted to see, in 4 weeks, Had a fabulous time. Mainly animals and pretty scenery, few stars. So, anything else? Okay, thank you. Okay.
Hi everyone, my name is Artash.
And my name's Arushi. So, a few weeks ago, we made a project called Deep Space Musical at the Space Apps Toronto. That's actually a hackathon, so you have 48 hours to solve a challenge. So, what our project does, our project takes an image from Hubble and converts it to music so that the visually impaired can also enjoy the beauty of the universe. This project actually won the NASA Space Apps Award.
Hi, so we all know the Hubble Space Telescope. The Hubble Space Telescope is launched in 1990, is actually going to turn 28 this year. And it's been taking over 1.3 million observations so far. So, and many of these observations we've already seen, like popular ones being the Pillars of Creation, or it's a visual telescope. And so, since its pictures are so interesting, we thought it would be a good idea to actually turn these pictures into music, so we can experience the universe in a different way. And the best thing, of course, is that it's people who are visually impaired and can't actually look at these images can also enjoy the beauty of our universe. So these are just a couple of the pictures taken by Hubble. So how did we convert this image into music? Well, first we took the RGB color image from the Hubble Space Telescope, in this case the Pillars of Creation. So then we took this image and converted it into grayscale. There. So after converting to grayscale, this is still a pretty big image, like thousands of pixels inside the image. And we can play each of these pixels in the image, because otherwise the music will be way too long and there'll be many non-eventful parts in the image. So after this, I performed something called pooling on the image. So basically what that does is it resizes the image here into a smaller image. But at the same time, it'll keep the main details inside the image. To do that, basically I take maybe of the grayscale image, I take a small part, and then I take the largest pixel value inside that part. And I repeat this for every this part, until I get a condensed image, this one. So to do this, I used Python, a programming language I use a lot.
So what I did is I took the numbers that he gave me, and then I assigned them a musical note so that you can actually play the music and then see the notes.
Yeah, since basically I had a matrix of many different pixels, I gave those pixel value to Arushi, and then she was able to convert them into frequencies, basically musical notes. So basically how it works is that each pixel in the image is played one by one. So first, the top corner pixel is played, you hear the note, and the brighter the pixel value, the higher pitched note you'll get. So our musical has 3 parts. The first part, of course, being the birth of the stars. So stars are born in, for example, nebulas, and so one of the very popular images is the Pillars of Creation. Basically, it's a bunch of gas inside the Eagle Nebula, M16, and that bunch of gas looks like a couple pillars, and it actually becomes lighted up, as you can see in this image, because of the radiation coming from the nearby hot stars. So now, I'm going to actually play the music for this image. So, before I play it, you'll notice that since we're playing each pixel, you'll notice that when we hit a higher pitched note, it means that we're reaching a star, like here or here. Of course, these stars are not actually inside the dust cloud. We're just seeing them because, well, they're much closer to us than the pillars of creation. So I'm going to play the music. Yeah, so that's a short example of the music, a little bit of the music. So you can see that there are not many sharp notes because, yeah, in this image, it's mostly just the big gas cloud, which is pretty much the same color and brightness. But each time we hit one of these stars, we get a higher pitched note. So the next image, after the stars are formed, then, of course, they'll form into galaxies. So this is a picture from the Hubble Ultra Deep Field image. So this was taken over a period of 2 weeks, actually, to get a good exposition. And so here's the image. There, it's basically a lot of clusters of galaxies. So now, in this image, unlike the previous ones, we don't have only a couple points of interest. We have many, many different galaxies. Actually, in this image, there was actually 10,000 galaxies that we could count. So now I'm going to play the music, and you'll notice that higher pitched notes are much more frequent now. Yep, there you go. And then the last part of our musical will, of course, be the death of the stars. So, stars, so this is the supernova 1987A. So, this used to be a blue hot giant star. And, you know, since blue stars don't actually live very long because they consume their energy much faster, being much hotter, it started slowly shedding out its outer layers of gas. And then eventually, so the gas was kind of forming a ring around the image. But then the supernova happened, of course. So a lot of radiation and a shock wave was burst out of the center of the star and then collided with the dust and the gas that had been released out of the star previously. And that's what lighted up those rings of gas around it, so we can actually see it when we look through it, the Hubble. So now I'm going to play you this image. But, you know, since the rings are lighted up by such high-level radiations, it's going to be very bright. So you're going to hear lots of very high-pitched notes in this image. So yeah, as you can see, so slowly what happened in this image is that it came here, it was pretty low-pitched sounds, and then suddenly it got much high-pitched, and then continued with high-pitch, low-pitch, high-pitch, low-pitch. So now that you've listened to each bit of each individual part, I'm going to play you the whole musical. So around 40 seconds from each image, so you can actually hear the whole thing together. Kind of how everything formed, galaxies, stars, galaxies, and the death of the stars. now, last one. And that is the whole musical all together. Thank you, and we would also like to thank the Royal Astronomical Society of Canada for keeping everyone excited about space and astronomy. So also this year has been very special for us. We've participated in many RASC events this year, and we continue to mention the Royal Astronomical Society of Canada inside our many presentations that we do and on our website. So this year we've won the Jesse Ketchum Award, and we've done many other presentations.
Yeah, I spoke at the Women in Planetary Science for women, and yeah.
And thank you.
Borrow the microphone so we can ask the question.
This is probably silly, but what does the 80 on your note staffs mean? It had number 80.
80?
On the where your notes are.
Oh, here?
There's no.
Oh.
80.
Oh, here?
Tempo?
Well, yeah. So we since we're playing notes in each of the parts in the musical, we just Arushi converted a small part, a small part of the beginning of each of the musical for each image into notes actually. So for the first bar here, these are a couple of notes that are played in the first image of the Pillars of Creation. Here, same thing. But you can see the notes are changing a lot. And last one, where you can see you're getting really high-pitched sounds.
First of all, I'm extremely impressed. This is amazing. The other question is, have you thought about condensing the three parts, if you like, into three voices in a three-part harmony so that they would play simultaneously, and how that would sound?
Yeah, we've not thought about that, but it could be interesting. But we did it like that because these three images, they form a sequence together. So the first one, the birth of the star, the forming of galaxies, and the death of the star. So we just thought it would be more rhythmic and sequential if we put all three images, 1, 2, and 3.
You mentioned that you won a NASA app competition.
NASA Space Apps, yep.
Space app, right. So what is the next stage then?
Yeah, so we won the NASA Space Apps Toronto this year with this project. So the next stage, since now we're a global nominee, we had to submit a 30-second video to NASA, and then they'll be looking at all the videos and selecting some of the best.
Very good.
Thank you.
something rather boring, and I have to talk about the election. No, not that one, but the one that's coming up in a few weeks. We are about to release the slate of candidates for. I want just to be announced to anyone here or anyone online that we are now accepting nominations from anyone in the Toronto Centre. If you'd like to join council, you require 2 signatures from members in good standing on your nomination form. Just hand it in to myself, the head of the nominations committee, or President Ralph Chu, and you have until 2 weeks before the AGM. Thank you. Oh, the AGM is December 12th. So I will be making other calls on the forum. The only problem is that because we only have one other meeting before the AGM, and that is our fairly large speaker night, I figured we might not have a chance to make this call at that time. So that's why I'm doing this now, just before we've released the nominations has released. We'll release the slate of candidates. We'll be doing this on MailChimp in the next few days. Ralph?
Meeting in 2 weeks' time is a speaker's night, and our speaker that evening is Professor Rainer Weiss from the Massachusetts Institute of Technology. Professor Weiss is a Nobel laureate in physics for 2017 for his role in designing the LIGO observatory, and he'll be talking about exploring the universe with gravitational waves. Now, all members who have a valid email address got a message from me by MailChimp with a link to a special web page on our website where you can register for up to 2 tickets for free. We have an allotment of 200 seats in the auditorium for this particular lecture, and you need to register for those in advance. We will be closing the list off when we either reach our full allotment of tickets, or if let's see, I think the Science Center's cutoff date is November 22nd, because we have to print the tickets. So the idea will be that when you arrive on the evening of the talk, you'll go to a special reception desk in the front building, and they'll have your name on a list and just give you a ticket at that time. Okay? Because it's a public event and the other 200 tickets are being sold to the general public, we're all going to have to pay for parking. So it's $5 for the car to enter the parking lot for that evening. But I'm sure it'll be an interesting talk. The moderator for the conversation after the lecture is Sarah Seeger, and she's coming up with Professor Weiss from Boston especially for this talk. So it should be a really great event. Okay, our next meeting after that is 12th December, which will be the Recreational Astronomy night, our last meeting for the year. And we'll have a short presentation that evening, Chris Vaughan doing Sky This Month, and Clay Davies talking about building a Newtonian telescope for visual wide field and air travel. I can hardly wait to see what he's got in store for us. And then following Clay's talk, we'll have a brief intermission while we set up for the annual general meeting. And that's where the election comes in. We have a number of councillors as well as members of the executive whose posts are up for election this year. And again, if anybody's interested in being nominated for a position, you can talk to either Tony Horvatin, who's the chair of the nominating committee, or myself, or to Tom about that particular bit of work. Okay, next solar observing is going to be on November 24th, and in the usual way, Sean will give the go or no-go on that either Friday evening or first thing Saturday morning. And I think this is probably the last of the solar observing sessions for the year 2018. What we've decided to do, we were trying this out this year to use full moon weekends or weekends near full moon, with the idea that that would free up people perhaps to you know, do other things other than come out to the telescope for solar observing. But it's been a moving target. It really hasn't made anything any easier, I think, to get volunteers or you know, do anything else. So we're going to go back to the first Saturday of each month starting in January, and that'll be a bit more predictable, hopefully. So again, Sean will be making the announcement, and thank you very much for all the work in organizing these events throughout the last few years. Okay, the others monthly observing events. I'll call your attention to, the City Star Party, the week of 12th to 15th of November. The first clear night next week will be the City Star Party at Bayview Village Park. And then we have a long wait till the next Dark Sky Star Party, first week of December. Again, first clear night. And again, there will be a no-go or go announcement on our media and the website in the usual way, probably in the late afternoon, to just let you know whether those events are going ahead. Car Observatory still operational. Ian Wheelband is up there this evening getting ready to do a library talk in Thornbury. The road's still open, at least for a little while, but once the snow flies, again, we'll go to winter mode, and that means that you park at the top of the hill on the road that runs in front of the observatory and then walk in because they don't clear the snow from that roadway during the winter. So it's still available, but you do have to do a little bit of walking. If you don't want to do that, and you're interested in getting a look at some new equipment other than for Hyperstar adaptations and so on, we do have a number of instruments available for loan, and again, we have a couple of our telescope loan managers, Mark and Peter, here tonight. If you'd like to talk with them about borrowing equipment, please feel free to do so. And finally, the usual invitation for the meeting after the meeting at the Granite Brew Pub down at Mount Pleasant in Eglinton. So please feel free to join a few of us down there after the meeting ends. So again, we'll see you in a couple of weeks, either here in person or online. Remember to get your tickets for Professor Weiss's talk online, and please be patient about it, because we are in the we've unfortunately gotten to the stage where we've had to upgrade the service on our website, and there's apparently been a bit of a mixed up on the links between that website and the national website where we validate your memberships. So if you cannot get onto the website to register for the tickets, try again in a day or so. Hopefully by then we'll have that technical problem solved, and we'll see you here then or online for Professor Weiss's talk. So have a safe trip home, everybody. See you in 2 weeks.